Okay, hello everyone. My name is Liang Liu. I'm from University of Pittsburgh. And it's my honor to present our work, LightML, a Photonic Accelerator for efficient and general purpose machine learning. And today we may have witnessed the rise of AI technology. And this work might standing on the perspective of the energy consumption. And under the technical report, the energy consumption of the AI is growing larger and larger. And when it reaches to 2030, it will spectacularly rise to 20 or 25% of the entire power generation. And the modern GPU are building upon the transistors, and they come with the physical limitations, such as the Joule heating and the electromagnetic interference. And in contrast, a new emerging technology is to compute with the light, and replacing the electrical current with the optical light. And the advantage is the neutral load energy cost and the high operating frequency. And it has been shown that even if scaled the frequency to up to 40 gigahertz, and the heat generation is still negligible. And in recent years, photonic crossbar has been demonstrated for its high energy efficiency in matching multiplications. And today, we'll spend some time to introduce the mechanism of the crossbar device. And we show an example of a 4x4 crossbar device, which have two directions of the input. In the horizontal direction, we will derive the match by 4 horizontal vectors, and each of them is sent to a row modulator and converted to the light signal. And the light signal will propagate to all units in this row. And similarly, in the vertical direction, the vertical vector is sent to the corresponding column of the crossbar. Within each cross point, the optical device will conduct a dot product. And for example, in the highlighted block, it is a dot product for the vector x4 and vector y1. And so the entire 4x4 crossbar will produce the output for the match x multiplied by match y. And in the previous work, it has shown that it's about 200 times more energy efficient than the transistor-based device. And next, we'll have a close look at how the dot product is computed in each unit cell. The first step is to convert the digital signal to the optical wave using the modulator. The light will first come from a laser source, and it passes through a modulator. The modulator will read a 5-bit digital input from the register, and then it will including 1 side bit and 4 mantissa bits, and encoding the input vector like the x1, x2, x3 to a sequence of light pulse. The amplitude of the light has 16 different scales, which can represent the 4 mantissa bits. And the side of the bit is presented as the relative phase of the light. And after we modulate the 2 vectors like x and y in the 2 sequences of light, and the second step is to make those 2 lights interact with each other. And then we will send it into the beam splitter to couple and decouple the lights. According to a difference in the reflection angles, the bottom light have the half wavelength slower than top ones. And it turns out that the superposition of the light in the top will be x plus y, and that in the bottom will be x minus y. And after we coupling these 2 lights, and we will direct them into the 2 photon detectors. And the generated column is the square of the amplitude, which is x plus y squared and x minus y squared. And by placing then the 2 photon detectors in the opposite direction, we'll get a multiplied output, for example, like x times y. And next, the charge will be sent into a capacitor. And by repeatedly feeding the entire vector sequence, the voltage will be accumulated in the capacitor and be the output of the dot product. And we will use another ADC to convert the analog voltage to the digital one. And based on this photonic device, we will propose the LightML, which is a system-level photonic crossbar device. And in the existing crossbar device, they primarily discuss about the match-wise operation, like the matching multiplication and MVNs, and which might not be capable to run a very complex AI application. And in our work, we will propose some other implementation method to achieve the variety of the AI function supported. And we highlight the contribution of this work. And the function in the blue color, although they have been discussed in the previous work, but we'll have make a more efficient implementation in this work. And the function in the yellow color are absent in the previous work, and we provide a solution for them. And in our design, we first develop a complete memory hierarchy with the detailed analysis of the bandwidth and the memory utilization. And second, we provide a photonic crossbar array with more functions supported, and we investigate the size, the precision, and introduce a set of the photon modulator to achieve more ML functions. And finally, we'll provide an optimized analog circuit. Here is the contribution of this work, and we'll start with the feasibility study. And first, in our prior work, we have fabricated a laboratory prototype. It is a 4x4 crossbar array. We have the microscope image of this device here. And each unit cell is about 100 microns. And we also collect the experiment result for the dot product of two light signals. The figure in the right just showing the temporal accumulation of the dot product. And these two lights present first is our measured output and the ideal output, which is pretty much close to each other. And because due to the limitation of our laboratory equipment, we cannot access to the realistic data for the industrial level device, which they might have be able to access more advanced technology. So we will also derive error modeling to analyze the capability of this device. And we analyze 4 major sources of the error source, and the flow of the error propagation is showing in the figure below. And the detailed computation can be found in our paper. And the result of the error modeling is showing this figure. And the y-axis is the relative error, and the x-axis is the length of the dot product. Intuitively, as the dimension increase, the signal will keep accumulating, but the noise will be canceled by each other. And we draw the red line to mark our minimal requirement to achieve about 5 bit accuracy. And the blue line shows the error rate under the most advanced technology that the industrial can access. And the highest position that can be achieved will be like 6 bits. And next, we'll talk about our proposed method to achieve those AI functions. And firstly, we'll discuss the implementation of the nonlinear functions, which will be very important in the AI computation, like the softmax function is widely used in the large language model. And the existing crossbar device does not support this. And the classical approach, for example, if we allocate a new computing unit, will be very expensive to deploy. First, we will cause actual error and area and energy, and most of them can only support a limited amount of nonlinear function. And additionally, this actual device also brings some inconsistency in the memory transportation. In this work, we propose to utilize the photonic crossbar to compute those nonlinear functions. And here we notice that light signal will be very easy to compute the sine or the cosine function. And based on the previous device, we need to introduce another phase modulator to generate a phase shift like delta phi on this signal. And then the coupling result will convert this phase shift into a cosine function. And when we're accumulating the difference between these two lights, and it will result like x times y times the cosine delta phi. And the delta phi can be easily adjusted by the phase modulator. And next, by having those capability to compute this cosine function, we can construct any arbitrary nonlinear function using the Fourier series. And the constructed function is showing here. So any nonlinear function can be a summation of a constant coefficient, ak, and a cosine function. Within the cosine function, there is a scaling factor, it's 2 pi divided by L, and the multiplier of the x. And this operation can be very easy to achieve in our crossbar device. And we can send the coefficient ak in the top of the device in the direction, and then in the bottom direction, we first calibrate the multiplier kx into the 2 pi range, and then send it to a phase modulator. And by placing everything here, the accumulated result will be exactly ak cosine 2 pi over L times kx, which is our desired nonlinear function. And next, we'll introduce our proposed scaling technique. And the scaling computation will be extremely important when using the quantization. And for example, during the quantization, each integer will be mapped into a floating point. And according to different scaling factor, in the different matrix or different layer in the AI model, there will be a different scaling factor, which might require very frequently scaling operation. And in our proposal, we'll apply this scaling by utilizing the analog converter, the ADCs. And when reading the analog voltage from the ADC, we can tune the reference voltage to scale those digital output. Here is an example. Supposing that we have an analog input that's 0.4 volts, and to scale it to the 5-bit integer with the scaling factor is 20, and the reference voltage will be calculated by the quantization range 16 divided by the scaling factor 20, which is the 0.8 volts. And we use the DAC to encode this voltage and send it to the ADC as a reference voltage. And the readout of the ADC will compare the input voltage with the reference voltage. And then output will be plus A. That's what we want. And next, we'll talk about some of our optimized systolic function. Here is our optimization for the linear layer, which is the matching multiplication building block. And we consider about this in two scopes. First, the linear layer in the AI application typically involve a ReLU activation and a batch normalization. And we need an efficient computing flow for them. And second, consider about the matrix is very large. We need also consider about a tailoring problem. Here we show the example of the proposed flow. Suppose that we have two matrices that are tailoring into 4 partitions. And we first compute the multiplication for each 2 submatrices and write the intermediate result into an on-chip buffer. So after the multiplication is done, we need to conduct the add operation to combine these 2 intermediate results together. For example, we need to add the matrix EA with the matrix FCs here. So again, we'll utilize the crossbar again to achieve the addition operation. We'll first read the elements that we want to add, and then feed into the same direction of the crossbar device. And it will coupling with a constant 1 signal in the other direction. And then the accumulating result will be there in the capacitor, which is our summation output. And moreover, we also integrate the ReLU activation and the batch normalization within this computation flow. We first apply the standard deviation via this ADC scaling unit. And then the mean is appended as another adder in the additional stage. And also, the ReLU activation can be achieved via the analog signal, and we apply a diode to filter the negative voltage. And we also have plenty of the implementation for the other functions, like the convolution function and something. And due to the time constraint, we might not be able to present them all today. So if you are interested, and you can just read our explore mode in our paper. And finally, we'll talk about our evaluation. In our evaluation, we'll adopt about a 128 by 128 crossbar device. And we list all the parts of our architectures here. And the total energy consumption will be less than 3 watts. And the area is about 310 millimeters square. And notably, the ADC will contribute the most majority of the energy consumption. And the rest of the optical device, like the laser source or the modulators, will only cost about 1 watt. And here, we list the comparison to the nowadays more popular device like the NVIDIA A100 GPU and the Google TPU V3. And first of all, our device does not rely on a very high advanced fabrication technology, but instead, we only require about a 28 nanometer technology. And due to this ultra low power consumption, our device can scale the frequency up to 12 gigahertz, which made the peak performance reach about 325 TOPS, and which can rival the NVIDIA A100 GPU. And when we compare the power efficiency, our device is 73 times more efficient than the NVIDIA A100 GPU. And we also conduct a simulation of the inference latency for some AI applications, such as the ResNet, the VGG, or MobileNet. And these 2 figures plot the relative latency. And for the ResNet model, our model achieves a similar performance as the GPU or TPU. And for the VGG or MobileNet, we can scale up to 4.5 performance gain over those GPU or TPUs. And that's all for the presentation. So thank you for your listening. And we can move on to the Q&A session.